I'm super happy to be around you today and discuss about a topic I have been working over the past year, and this is next generation graph transformers. So this is a joint work with some amazing collaborators, of course, Jure and Evelyn from Stanford, and Stephanie and Alejandro from MIT and the University of Pennsylvania. Now, over the past few years, we have observed an unprecedented success of deep learning models, of deep learning methods, especially when it comes to processing data that are of the form of a sequence or of the form of a grid. So previously, Vasilis and Rishi emphasized on the power and the success of large language models in processing and manipulating text, or more generally, natural language. And I think Jan and I will later discuss the power and the success of large models in learning from biological sequences. And of course, we have all observed the success of computer vision and image processing tools or image processing methods, especially with a large amount of data. Now, a fundamental component of the success of these deep learning models is without the doubt the transformer architecture, which is, as you can see, illustrated in this super famous diagram. As you can see, the transformer architecture consists of several parts, and arguably those that drive most of the performance are two. One is the self-attention, which is a form of a nonlinear projection, or if you like, a form of a nonlinear convolution, and the positional encoding, which, as the word says, it encodes the position of each token in the sequence when we talk about text, and the position of each token in the grid when we talk about images. Now, long story short, the transformer is an amazing tool. And graph aficionados as myself, and I believe many of you here, are very interested in somehow leveraging the power of the transformer in doing machine learning and deep learning on graphs. However, when it comes to processing or learning with graphs, things become very tricky. And there are many reasons behind that. One of them is that graphs usually have multiple and diverse modalities of information. So they have at least two. They have information at the entity level and information at the graph level, which is the graph structure. For example, in a social network, we have the images and the text at the user profiles, and also the connectivity information between different users. So we know who is friends with whom. And also, if we look at molecular graphs, we have the type of atoms or functional groups, which is the entity-level information, the entity-level signal, and we have the bonds between different atoms, or the bonds between different functional groups. So on the one hand, we have the entity-level information, which is usually text. It is an image or a categorical variable, and we know how to effectively process and learn from them. And on the other hand, we have the graph structure, which processing it becomes very challenging. So the goal here is to jointly process these two modalities of information, the entity-level signal, but more importantly, the graph structure using a transformer. So in order to understand how we can do that, let's take a step back and observe or somehow look deeper into the hidden structure of sequences and images. To be more precise, let's look at this sentence here. The cat ate sushi, whatever that means. And if we consider, or if we think of a sentence as a sequence of tokens, it is easy to see that this sentence has actually a hidden graph structure, which is the line graph. Long story short, each token is connected to the previous token. So what happens to the transformer? The transformer takes the words or subwords and represents them into tokens. And then it encodes the structure of the sentence, or in other words, the syntax, using positional encodings. So the text positional encoding encodes the order of the token in the sequence. And something similar happens when we look at images. We can consider an image as a set of pixels. And if we do so, we will see that this pixel have a hidden graph structure, and this is the grid graph. Again, long story short, we have pixels that are connected to nearby pixels. Now, what happens again in the transformer is that pixels are represented by tokens, and then the transformer encodes the structure of the image or the pixel position using positional encodings. In other words, image positional encodings somehow encode the position of the pixel in the two-dimensional space. Now, the point I want to make here is that the transformer architecture explicitly encodes the graph structure, which is, in that case, a very specific graph structure. It's the line graph or the grid graph using positional encodings. Now, a very natural question is that can we actually design positional encodings that effectively encode the structure not just of line graphs or grid graphs, but of arbitrary graphs, of graphs that have a very abstract or complex structure, like the graphs I show here. But we are not only interested in finding any positional encoding, we are interested in finding positional encodings that admit four favorable properties. Property number one, we need them to be expressive, meaning that they should somehow encode as much information from the graph as possible. We want them to be equivariant so that they can be generalized across unseen graphs. And we want them to be generic, so not tailored to a specific domain, but applicable to multiple domains. So the final property we would like our encodings to have is to be scalable. Because many encodings work very well for small molecular graphs, but we actually are in need of positional encodings that can be applied in larger graphs. And if we go back to the question, can we actually design or learn such positional encodings, the answer that admit these favorable properties, the answer is yes, and later in this presentation I will try to show you how. But before I do that, let's discuss some prior work. So researchers have studied positional encodings for a few years now, I would say 3 to 4 years. And state-of-the-art methods are using eigenvectors of the graph Laplacian as node positional encodings. So for those of you that are not very familiar, the graph Laplacian is a matrix that encodes the graph structure. It encodes local and global properties of the graph. And what happens is that the eigenvectors of the graph Laplacian somehow inherits these very nice local and global properties. Now, when a graph has n number of nodes, it usually has n distinct eigenvectors. And the number of eigenvectors we are using to somehow design these positional encodings is a design choice, but not just a design choice that somehow defines the properties of the positional encodings. To be more precise, we can have positional encodings that look at all the eigenvectors of the graph Laplacian, and these positional encodings have very high expressive power, they are generalizable, they are generic, and however, they need cubic type complexity, and they need quadratic memory complexity. Now, there is a way to overcome this limitation of the complexity limitation, and this is to compute, let's say, a subset of eigenvectors, so the top k, let's say, or the bottom k eigenvectors. And these methods work very well, and they have a approximately linear complexity. However, they work well in practice, but they have a little bit less or lower expressive power, a little bit lower generalization ability because of stability reasons, and they add some sort of inductive bias because different eigenvectors or different number of eigenvectors means different things for different graphs. Now, in the remaining of the talk, what I will do is I will propose a novel positional encoding framework that leverages the power of message-passing graph neural networks to somehow compute eigenvector-based positional encodings that have high expressive power, they have high generalization ability, they are generic, but they are, as I said, they are eigenvector-based, but they can be computed with 1 order or 2 orders of magnitude lower computational complexity. So I have 2 slides of analysis, very simple things. So Josh gave you a primer on graph neural networks. So a graph neural network layer looks like that, where x of v is the embedding of node v, and we consider the embedding of node V at layer L and at layer L minus 1. And the update for node V takes into account the update of node V at the previous layer and also the embedding of the neighbors of V. And the way they do, the way the message passing graph neural network does that is that it uses two functions. One is function f, which aggregates information from the neighboring nodes. And there is a function g that combines information from, of each vertex with the aggregated one from the neighboring signals. Now, the reason why I include this equation here is because we have a very nice observation, a very nice remark. And this remark is the fact that the graph neural network layer, the graph neural network update, can also be viewed as a nonlinear function of eigenvectors. So to be more precise, we have this update here, and this update is exactly a nonlinear function h, which can be an MLP, of the eigenvectors V. So V is the matrix of eigenvector, and this function is parameterized by the update of V at the previous layer and the update of neighbors of V. So actually, this observation is pretty cool because it implies the following. It implies that maybe there is no need to compute eigenvectors with the complexity, some complexity problems, but we can use message passing graph neural network to learn positional encodings that somehow imitate eigenvectors. So that is the idea. And this is our proposed, or the high-level, somehow illustration of our proposed Perl architecture. So what happens here is that we have the input graph that has some node attributes. So we use these node attributes as initial tokens for the graph transformer. And then what we do is we remove the node attributes and use a message passing graph neural network to only process the graph structure. Now, for those of you that are super familiar with message passing graph neural network, you might wonder the following. You might say, okay, I mean, message passing graph neural network work great, but when it comes to processing graph structure without node attributes, there are certain limitations, structural limitations, what we call WL limitations. Now, in order to overcome, and this is actually true, however, there are ways to overcome these limitations. And today I will not tell you how, or I will not tell you why, but I will tell you a way to overcome this limitation. So the way that we'll do that is that we'll somehow generate some synthetic node attributes, initial node attributes, which will break some symmetries and allow message passing to unleash the true potential, the true expressive power. But to be more precise, let's zoom in into this part of the architecture. So what happens here, is that, as I said, we have the graph that has some initial node attributes, and then we remove this node attribute, so we only have the graph structure. And then for each node in the graph, what we will do is we will associate each node with an M set of samples, M set of values. So we'll draw M samples from a probability distribution for each node. So this, for example, if we look at node 4 here, we will draw M different values. So we'll have, I don't know, let's say 0.1, 0.2, 0.3, which are these new node attributes for node 4. And we'll do the same for every node in this graph. And then each of these samples for all the nodes will be processed independently through a graph neural network to produce an output encoding, an output representation. So for each sample, we have a corresponding output. So what we have achieved here is, as I said, somehow break the symmetries using this randomness. However, there is a caveat that we somehow violate the equivariance or the generalization of the model. And there is a simple way to reconcile for that, to overcome that, and this is by using this pooling function rho here. So what we do is, again, let me recap, is that we draw random samples for each node. We pass these samples independently through a message passing graph neural network that breaks symmetries and increases expressivity, and then we use a pooling function that maintains the symmetry, but at the same time, it is expressive enough for our purposes. So To recap, this is let's say, the high-level picture of our proposed Perl architecture, and it has some very interesting properties. As I said, it has high expressive power. It can compute cycles and code cyclics that are super important both for molecular graphs and social networks and other types of graphs. It is equivariant, which means it can generalize across new graphs. And it is generic, so it's not tailored to a specific domain. And what is super cool is that the computational memory complexity is O m times n. N is the number of nodes, m is the number of samples. And the number of samples for large graphs can be much lower than the number of nodes. So it's kind of independent from the size of the graph. So now we test our proposed approach in two tasks. One is on small molecules, and what we are doing here is we're trying to predict a specific molecular property called log P, and we are using the zinc, the famous zinc dataset for that. So in terms of a graph task, this looks like a graph regression task. And you can see here now in the y-axis we have a method that doesn't use any positional encodings, a method that uses Laplacian positional encodings, another one which is an invariant version of Laplacian positional encodings, and our proposed method which is called Perl. As you can see, our proposed method is almost, I would say, 3 times or 2 times better than methods without positional encodings, and somehow 20% better than the best competing alternative. And the next task is graph classification, which uses kind of larger data with larger graphs. So the task here is to classify social Reddit graphs according to the thread type. So in terms of a graph task, this is graph classification with 5 different classes. And as you can see, here I present the classification accuracy, higher is better. And again, we have a similar picture. We have a big benefit compared to no positional encoding, and some also very, very interesting benefit compared to the competing alternatives. And with this slide, I will conclude my talk, and I'm ready for any questions that you might have.
Hi, great talk. Thanks. Is the pooling function in a way kind of a memory of what the...
Depends. So what we are using here is summation. So you can do it online. You don't need to have a memory necessarily. Right. You need to have a memory of the current, let's say, estimate of the pooling, of the current estimate of the summation. So it's not too big of a deal.
Okay, thanks.
Yeah. I don't think that people could hear you. The question is, if we need to train the positional encoding for its dataset, or there is a, let's say, unsupervised or self-supervised way to do so. So for our current results, we train for its dataset, but there is nothing that prohibits us from training in an unsupervised link prediction manner and learn this type of embeddings or positional encodings. Yeah.
One last one. Great talk. I have a question regarding the spectral clustering thing, the spectral embeddings, positional embeddings thing. You said essentially you try to imitate the operation that the Laplacian is trying to achieve. And essentially my question is twofold. First of all, when you say imitate, do you mean in some sort of like formal kind of imitation, or essentially you just try to completely replace it with something that's more efficient and flexible without any sort of theoretical underlying connection? Yeah, actually this was the first part. And
so I don't remember if I used the word imitate. Maybe it's the wrong use of the verb. So we're not exactly imitating. So what we're doing is that we first observe that a message passing graph neural network is actually a nonlinear function of eigenvectors, either of the graph adjacency or the Laplacian, depending on your somehow message function or aggregation function. And what we're saying is that there is no need to bother about imitating anything or computing any eigenvectors. You just run your model with the approach I showed you, your graph neural network, and this graph neural network will learn to produce positional encodings which are nonlinear functions of eigenvectors.
I see, I see. So essentially, I'm trying to understand where the performance gains are coming, and I'm wondering whether essentially using the Laplacian itself is more than a hindrance in getting better performance or not. And,
So that's a good point. So the performance, I think, is coming from the fact that you allow your model to learn from the data, and you don't somehow impose a specific bias to the data. So it's a completely generic architecture. And the second thing is that the model has the right biases and the right complexity to be trained with the right amount of graph data.